Dear students, today we are going to discuss the concept elementary transformations related to the topic matrices. Elementary transformations are very useful to find out the inverse of a matrix, of a square matrix. So let's begin. See, there are three elementary transformations of a matrix. They can be used on rows and columns. Okay. We will see this one by one. See here. First elementary transformation is interchange of any two rows or any two columns. See, elementary transformations can be used on rows as well as on columns. So interchange of any two rows or any two columns is a first elementary transformation. So see here, if we interchange ith row and jth row of a matrix, then after this interchange, the original matrix is transformed to a new matrix. See here, if we interchange any row, suppose ith row and jth row, if we interchange for a particular matrix, then after this interchange we will get a new matrix. Okay, so let us see here symbolically how will you denote that transformation. So this transformation is symbolically denoted as ri suffix I, means row number, means ith row interchanges to jth row. It is denoted as r for row and I and j are suffix which denotes the row number. Okay, so ri changes to ri interchanges to rj. It can be also written as r suffix ij. So row number I and j are interchanged. Okay, see here, the same transformations can be applied to two columns. Say, suppose letter C is used for column, so Ci interchanges to Cj, or you can write Cij like this. Okay, so you can interchange any two rows or any two columns if as per your requirement. Okay, so this is called as elementary transformations of a matrix. Okay, so for example, let us see one example. Suppose matrix A is given, square matrix 5 7 3 2. Then see here, R1 interchanges to R2, row number 1 interchanges to row number 2. So it gives a new matrix like this 3 2 5 7. Okay, so this is very important elementary transformation. Okay, all this is used for to get the inverse of a matrix. Remember that we will see in next lecture, but before that what are the elementary transformations related to matrix, that we will study. Okay, so this is the first elementary transformation, remember. Now next one, multiplication of the elements of any row or column by a non-zero scalar. See, this transformation says that you can multiply any non-zero scalar. Non-zero scalar means any constant, non-zero constant number. You can multiply that number, or you can say non-zero scalar, to any row or any column. So multiplication of the elements of any row or column by a non-zero scalar. Let us see in detail. Suppose if k is a non-zero scalar, means k is a constant, any constant, non-zero constant, and suppose row ri, ith row is to be multiplied by a scalar k, then we multiply every element of ri by the scalar k. So this is the multiplication between any non-zero scalar with any row. So that k gets multiplied with every element of that row. Okay, so remember this. So then we multiply every element of Ri by the scalar k. Now this transformation is symbolically denoted as k into Ri, like this. See here, k is multiplied with row number I, or you can write Ri into bracket k, like this. Generally we use this symbol. Okay, remember. So same can be applied for column. So you can write k into Ci or Ci into k, like this. For example, let us see one example. See here, a matrix A is given, 3 by 3 matrix, order 3 given to you. And suppose if you want to multiply row number 1 by 2, 2 into R1, 2 is called as non-zero scalar. 2 into R1 gives a new matrix. See, just you multiply every element of row number 1 by 2. So it gives 4 minus 2, 6. Other two rows remains as it is here. No change in the row number 2 or row number 3. Only you have to multiply by 2 to the row number 1. It gives a new matrix like this. So this is also an important elementary transformation. You can apply it for column also. Okay. So just I have given one example related to row. Now next elementary transformation is adding the scalar multiples of all elements of any row or column to corresponding elements of any other row or column. So it says that it is the addition of scalar multiples of all elements of any row or column. Just you think about row, it is applicable for column also. Adding the scalar multiples of all elements of any row to corresponding elements of any other row. Okay, so let us see in detail. Suppose if k is non-zero scalar and the k multiples of the elements of Rj or Cj, Rj for row, jth row, and Cj for jth column, but here we will discuss only for row, so don't think about this. Just see row Rj are to be added to the elements of Ri. Then the transformation is symbolically denoted as Ri changes to Ri plus k into Rj, or for column like this. See in detail, I will explain in detail. See what happens here. Row number I changes to. How will you change the row number I? Like this here. Ri plus k times Rj means you take the row number j, multiply it by scalar. Row number j gets multiplied with the scalar k, and just you add to the every element of Ri. So there is a change in row number I. Just you use the row number j, means multiply by k and add to this. So adding the scalar multiples of all elements of any row means here adding the scalar multiple k into Rj to the corresponding elements of any other row. Any other row means here Ri. So Ri plus k into Rj, like this, or it is same as for column also. We will see in detail by one example. Okay, so suppose matrix A is given 2 by 2 matrix like this, and I want to change the row number 2 as R2 changes to. See, this arrow shows that R2 is changing. R2 changes to R2 plus 2 times R1. So we have to change row number 2 only by adding 2 times of R1. So what happens? See here, row number 1 is as it is. Remember, no change in the row number 1. Just you use the row number 1 here. See here, so row number 2 changes, R2 changes to, see here, original element is minus 3. Just you add plus 2 times 2. 2 times 2 means this is 2 times R1. So 2 times 2 corresponding element is added. Similarly here 1 plus 2 times 3. 2 times 3. So row number 2 changes as per this transformation and it gives another matrix like this. Row number 1 as it is. See, again and again, row number 1 remains as it is and row number 2 changes. It gives 1 7. See, R2 changes to R2 plus 2 times R1. So scalar multiple of any other row is added to the corresponding elements of any other row. Remember this. So it gives a new matrix. Remember. Now see another example. Suppose B is the matrix given here like this. And if you want to perform a column transformation, or if you want to change the column number 2 here, C2 changes to, so I want to change column number 2, see here, as C2 plus 2 times C1. Okay, so what happens? See, column number 1 remains as it is, see here, 4 2 as it is, and we have to add 2 times C1, so minus 3 plus 2 into 4. Similarly here minus 1 plus 2 times 2, so it gives 4 5 2 3 like this. So column number 1 remains as it is and column number 2 changes. Okay, so this is the adding the scalar multiples of all elements of any row or column to corresponding elements of any other row or column. So these are all 3 elementary transformations. Now let us take a note here. See here, number 1, after the transformation Ri changes to Ri plus k into Rj, Rj remains same as in the original matrix. Just in this example we have seen this, no change in Rj, we have to change Ri, just adding k into Rj. Okay, so Rj remains same as in the original matrix. Similarly, with the transformation Ci changes to Ci plus k into Cj, here Cj remains same as in the original matrix. Okay, just that by that previous example I have explained it in detail. So just as a note, you can remember this. Now second note, see here, the elements of row or multiples of the elements of a row cannot be added to the elements of a column or conversely. Means if you want to perform a row transformation, do not use column, or if you want to use column transformation, then do not use row. Okay, so row transformations are applied for row only, elements of row only, and column transformations are useful for or to change the column only. Okay, so don't mix up row and column together. Okay, so that is very important to remember. Now see another concept, another note, that when any elementary row transformations are applied on the both sides of A into B is equal to C. See here, this is one equation given in the form of matrix. It is called as matrix equation. So if you want to apply elementary row transformations to this equation, then the prefactor A changes. This is called as prefactor. Here A into B, in that A is called as prefactor. Prefactor A changes and B remains unchanged. Okay, so and the same row transformations are applied on C. So this is very important. Here if A into B is equal to C is given to you, this is the equation, matrix equation is given to you, and if you perform the row transformation on both sides, then only prefactor changes, and here on the RHS C changes as per that row transformation. So equality remains as it is when prefactor changes, and that on the RHS C changes. Okay. Similarly, if you want to apply elementary column transformations on this equation, then post factor B changes. See here, post factor B changes and A remains unchanged, and the same column transformations are applied on C. So what happens here, whenever you apply row transformation to this matrix equation, then A changes, means prefactor changes, and right hand side changes. And in case of column transformations, post factor, that is here B, changes and C also changes, no change in A. Okay. So this is very important. Property number 3 and 4 are very important. Now see here, I will explain it by example. So for elementary row transformations, what happens here? Suppose the matrix A is given, B is given to you, and A into B, that is suppose C is given like this. Check this, A into B is this, and the equation, that is A into B is equal to C. This is called as matrix equation. Here it is A, B, and it gives AB, means that is called as C here. So now if you apply, if you write this equation in the matrix form like this, here A as it is, A is written here, B is given, it is equal to C. So this is called as a matrix equation. Now if I apply a row transformation, okay, if you apply row transformation here, then R1 changes to R1 plus 3R2. You can change any row, any column. Here we are using elementary row transformation. So suppose I select that R1 changes to R1 plus 3R2 like this. See what we get on the both sides. Remember, on the both sides of this equation, only prefactor changes. See here, there is a change in prefactor, no change in the B. B remains as it is. This matrix changes, also this matrix changes. Then equality remains as it is. Remember, this is a equation. AB is equal to C is one equation. And if you perform the row transformation on both sides, then if you apply the row transformation, then only prefactor changes. Prefactor changes means what? If you want to apply R1 changes to R1 plus 3R2, then apply it for prefactor, means here you apply it for a matrix A only. Do not apply it on B, because if you apply for B, then this equality does not remains as it is. Okay, so there is a change in A, also there is a change in C. See here, R1 changes to R1 plus 3R2 on both sides. So it gives this, here it is 10, 14, row number 2 as it is, and B also as it is, and here it gives 4, 70, 120 as it is. So that means now if you apply this, see this is a new matrix B as it is, and it is equal to this matrix. Now if you want to verify this, then check this product. This is new A, new matrix A into B as it is, and it gives a new matrix C. So from this equation, after this transformation, we get this equation. So in this case, when if you want to apply elementary row transformations to the equation, to the matrix equation, then on the LHS you change the prefactor only, and on the RHS that C will change. Okay, so it shows that prefactor A changes and B remains unchanged by this example. You can verify this by multiplying these two matrices. You will get this answer. Okay, do not change B, only prefactor is changing here and RHS is changing. Okay, remember. Now what happens for column transformation? I will take same example. Matrix A is given, B is given, and A into B is this. Okay, that is equal to C. And suppose matrix equation is given, that is A into B is equal to C. And if you want to apply column transformation, any column transformation, first of all, that equation is given in matrix form like this. A keep as it is, B is given here, and it is equal to C. Suppose I want to use this column transformation. See, C1 changes to C1 plus 2 times C2. So I have to change column number 1. Here also column number 1 by this transformation C1 plus 2 C2. Now in this case, this is called as post factor. B is called as post factor. A remains as it is. See, A as it is. I have to change this post factor. So minus 1 plus 2 into 0. Here 1 plus 2 into 5 like this as per this. Column number 2 as it is. Here also 1 plus 2 into 10 and 1 plus 2 into 20. Column number 2 as it is. So it gives, now A remains as it is. Post factor changes to, see here, minus 1, 11, 0, 5, and here 21, 41, 10, 20 as it is. Okay, so we get a new equation. Here A remains as it is. Post factor B is changing here, and C is also changes. Now if you check this product, see, A remains as it is. We have to keep A as it is. Only post factor is changing in this equation, and it gives the RHS. Now if you check this, actually if you take this product properly, then you will get this answer. So equality remains as it is. While performing elementary column transformations, you have to change post factor only. Okay, so here in this case it shows that post factor B changes and A remains unchanged. So in this case, always in case of matrix equation, if you want to perform row transformation, then prefactor changes, and in case of column transformation, post factor changes. That is very important property or important note. Okay, and these are called as elementary transformations, elementary row transformation as well as elementary column transformations. So this is all about this. Okay, so I hope you have understood all elementary transformations and all remaining notes related to this. If you want any doubt, if you have any doubt related to this, then contact me on my personal number. Okay, thank you.